Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE314 Measurements and Instrumentation. This is the second lecture of week 13, your lecture number 42. And in this lecture, we are going to discuss about this is the second part of your design problem based examples. And we are going to solve problems based on digital signal conditioning systems. So let's get started with our lecture. Okay, so here is your first design problem. The problem states that consider a comparator circuit given below with a positive feedback connected to the positive input of the device. So this is your circuit and the Vin is connected to the negative input while the positive input is connected with a feedback through a voltage divider R1 and R2. A sinusoidal input of plus minus 10 volts peak to peak is provided at the inverting input starting at time 0. So this is your input right here. Starting at time 0, it is a sinusoidal input and it goes from 0 to 10 to negative 10 and so on. So it is a continuously time varying input. Draw vertical lines between the input waveform and the output waveform. So here this is your V out. This is your V out. And what we have to do is we have to draw lines like this and we have to draw our output corresponding to this the changing input on this plot. And we have to label the values of voltages on our output as well. The values of R1 and R2 are 1 kilo ohm and 9 kilo ohm respectively. So this R1 is 1 kilo ohms and this R2 is 9 kilo ohms. We can see from here that this is sort of a hysteresis comparator and the supply voltage of this comparator is plus minus 10 volts. So your output cannot be more than this. If your positive input is greater than the negative input, a positive 10 will come at the output and in the other case, a negative 10 will come at the output. So your output is going to be switching between positive 10 volts and negative 10 volts only. So this analog portion will be eliminated and it will be a square wave. So let's see at which point in time your output will switch from positive to negative and from negative back to positive. At t is equal to 0, V in is equal to 0. This implies that V out will be equal to 0. And at t is equal to 0 plus, just after time 0, your V in is greater than 0. It is in positive direction as we can see here at this point. So this implies that your V out will be equal to negative 10 volts because now your negative input is greater in magnitude than the positive input. And your V plus, the voltage here, will be equal to negative 10 into 9 over 1 plus 9. So your V plus is equal to negative 9 volts. And we can see here that your V in is greater than 0. It is positive and your V plus is less than 0, that is with a negative sign. So your V in negative is greater than V positive. This implies that your V out will remain equal to negative 10 volts at t is equal to 0 plus. So we can write here with a blue pen that this is negative 10. Now, as far as this V in remains in positive region, it will be greater than your V plus because your V out will be continuously at negative 10 volts and your V plus will be continuously at negative 9 volts. So for this whole region, your V out will remain equal to negative 10. Now, from this point, your V in will drop below the 0. So it will go into the negative magnitude. And at what point this V in is going to become less than this V positive. Our V positive is negative 9 volts. So up till here, let's call it negative 9 volts. Up till this point, your V in will remain greater in magnitude than your V positive. So your V out will remain equal to negative 10. And as soon as your V in, your V negative drops below negative 9 volts, your V positive will become greater than your V negative. So at this point, your output will shift from negative 10 volts to positive 10 volts. So now, until V negative is greater than V positive, V out will remain equal to negative 10, and until V positive is greater than V negative, V out will be equal to positive 10. So what is the value of V positive now? At this point, at this green point, V positive is equal to plus 10 into 9 over 1 plus 9, and V positive is equal to plus 9 volts. So your output will remain equal to plus 10 volts until your V in reaches again a positive 9 volts. So up till this point, your V out will remain equal to positive 10, and then it will drop back to negative 10 volts at this point. So at plus 10 plus 9 volts and at minus 9 volts, your V in will keep switching. So this is going to be your output voltage. It will switch from negative 10 to positive 10 volts when your input switches from negative 9 volts below negative 9 volts, and it will switch from positive 10 volts to negative 10 volts when your V in switches above positive 9 volts. So this is going to be your final waveform. So this was a fairly simple problem, a bit tricky. You have to be very careful while dealing with the varying inputs in time, and you have to be careful that at which instant in time the change in input will cause a shift in output, switching in output from positive to negative and negative to positive values as a result. So let's now move on to the second problem related to digital signal conditioning circuit design. The problem states that a 12-bit ADC with a 6-volt reference and a conversion time of tau c is equal to 10 microsecond is available. What we have to do is we have to calculate the maximum frequency of a sine wave that can be converted into a digital signal without any error. And this is the formula of the limits that defines the maximum frequency of your change in input with your conversion time and your step voltage delta V. So now our VR is equal to 6 volts as given reference voltage. Tau C is equal to 10 microseconds, that is again given. N is equal to 12 bit, and V in is equal to V naught sine omega t, where V naught is equal to 3 volts, that is again given here. Omega is equal to 2 pi f, we know that it is the angular frequency, and f is equal to question mark. We have to find the maximum frequency f. So let's use this formula. dV in over dt should be less than or equal to delta V over tau c, and that is equal to VR over 2 raised to power n tau c. So this implies that d into V naught sine omega t over dt should be less than or equal to 6 volt over 2 raised to power 12 into 10 microseconds. seconds. And this gives us, and the differential of this is V naught omega cos omega t should be less than or equal to 6 over 2 raised to power 12 into 10 into 10 raised to power minus 6. And this implies that this term, the input voltage, will be maximum. The V naught omega cos omega t will be maximum when cos omega t is equal to 1. We all know that. So let's substitute 1 for cos omega t and we get V naught omega should be less than 6 over 2 raised to power 12 into 10 into 10 raised to power minus 6, and this implies that 3 into 2 pi f should be less than or equal to 6 over 2 raised to power 12 into 10 raised to power minus 10, and this gives us f should be less than or equal to 7.77 hertz. And this means that your input signal frequency, that was a sine wave, should have a frequency lower than 7.77 hertz to utilize the full resolution of ADC, 12-bit resolution. If we have our input voltage frequency greater than 7.77 hertz, the 12-bit full resolution of ADC will not be used and there will start coming errors of 1 bits or 2 bits LSBs, and our effective resolution will become lower than 12 bits. So it may result in an effective 11 bit or 10 bit or 9 bit resolution of ADC. So we are not right now talking about the sampling frequency or the Nyquist frequency. We are just talking about the utilizing the full range or full resolution of our ADC. So again, this was a simple problem, relatively simple problem, and I don't think there should be any issue in understanding this. But these things are at the same time very important, and they should be considered while sampling or converting your analog signal into a digital signal using ADC and then using it in your feedback loops. So it happens many times that your ADC is not supporting your very quickly changing input signal from the sensor, and that input signal from the sensor is used as a feedback in a control loop, and your control system is behaving in an anomalous way, and you are not understanding why, because everything else seems fine, but you have not considered this limitation of frequency, the maximum frequency of the input voltage, and all the error is coming from the conversion from an analog signal to digital signal. So do keep these conversions in mind while designing your process control systems. Okay, so let's start with your third design problem related to digital signal conditioning. The problem states that we have to design a hardware for a liquid delivery system, alarm system that provides a binary high output when the system temperature is between 40 to 50 degrees and the flow range is between 2 to 3 liters per minute. So we are using two sensors. One is a temperature sensor and one is a flow sensor. The output of temperature sensor is given here and the output of flow sensor is given here. So this is your temperature sensor and this is your flow sensor. The temperature sensor is a resistive sensor. So a change in resistance will occur when the temperature changes according to this given expression. And the flow sensor is a voltage based sensor whose voltage will change when the flow rate will change. So let's first define a few variables. The TH that corresponds to high temperature, TL that corresponds to lower temperature. Your higher temperature is 50 degrees Celsius and your lower temperature is 40 degrees Celsius. And then again for the flow you have QH, higher value of flow, and that is 3 liter per minute, while QL corresponds to lower value of flow, and that is 2 liters per minute. Now the tricky thing about this problem is that we don't just have to turn our alarm system on when the temperature exceeds a certain limit or exceeds a certain value. Rather, we have to turn our alarm system on when your temperature is within a given range and your flow is within a given range. So your output should be high if TH bar dot TL dot QH bar dot QL. This means that when your temperature is higher than the lower value of temperature of that range, your alarm system will turn on, but it should turn off when it is higher than the higher value of that range, higher limit of that range. So giving TH bar here, and same goes for your flow sensor. Now let's find out what are the corresponding values of resistances for the given two values of temperature for the given range, and what are the two values of voltages for the given two values of the flow range. So your at TH, RTH will be equal to 1000 into e raised to power negative 0.05 into 50 minus 25, because right now we are considering the temperature to be 50 degrees, and that gives us RTH is equal to 286.5 ohms. Similarly, at TL, RTL will be equal to 1000 into e raised to power minus 0.05 into 40 minus 25, and this gives us RTL is equal to 472.4 ohms. And from here we can see that this temperature sensor has a negative temperature resistance coefficient. Then moving on to the flow sensor, at QH, VH is equal to 5 over 3 plus 5. This gives us VH is equal to 0.625 volts, and at QL, VL is equal to 5 over 2 plus 5, and this gives us VL is equal to 0.714 volts. We have to use 4 comparators. For a single value of temperature and a single value of flow, we had to use 2 comparators, one each for one value of temperature and flow. But for the ranges, we have 2 values of temperature and 2 values of flow, so we have to use 4 comparators, one for each value of temperature and flow. The good thing is your output of the flow sensor is already in voltage, so it can be directly used with a comparator. But in case of your temperature sensor, the output change is in the form of change in resistance with respect to change in temperature. So we have to convert these two resistances into the change in voltage to make them compatible with use with the comparators. So let's convert these resistances into voltages by using a potential divider. So here is your potential divider. Let's power it up with a 5 volt supply. Keep the fixed resistance R at 500 ohms, and here this is your temperature sensor RT, and this is your VT. So this gives us VTH for temperature sensor equal to 3.18 volts, and VTL for the lower value of temperature to be equal to 2.57 volts. Now we have voltage outputs for both temperature and the flow sensors. So let's proceed with making the actual circuit and implementing this Boolean expression that we just derived here in this box as equation 1. So let's just use 4 comparators for 4 values. These two are for temperature sensor and these two are for flow sensor. positive, negative for all these comparators. Now, in case of temperature sensor, these are for temperature sensors. So one of our voltages is 2.57. This is 3.18. And in case of flow sensors, we have our voltage, reference voltage equal to 0.714 volts, and our other reference voltage equal to 0.625 volts. And here we have our, on the positive input terminals, we have our V temperature, and here on the positive and negative inputs we have our V flow. And the final expression would be, what we wanted was TH bar. So TH corresponds to this value, so let's invert it, and TH, so let's use it as it is here and here. And in our final expression again, it was QH bar, and that corresponds to this 0.625 volts. So just invert it and use it as it is, and then just AND them together. So this is your AND gate, and this is your V out to the alarm system. So this example just demonstrated how to use comparators with for the ranges of inputs, not for just one value of input. You have a complete range of temperature, and only when the temperature is within that range, your input should be high. So there is a lower limit and a higher limit. When your temperature is greater than the lower limit and less than the higher limit, your temperature is within the range and your output should be 1. And as soon as your temperature is either lower than the lower temperature limit or higher than the higher temperature limit, it is out of the range and your output should be 0. So you have to use two comparators for one parameter. And in this example, we had again two parameters and both for the ranges. So we are using four comparators for the four boundary conditions provided for the temperature and the flow rate. And lastly, let's move on to the final example of today's lecture, that is related to the digital signal conditioning circuit design. And the problem states that an LDR's resistance changes linearly from 3 kilo ohms to 1 kilo ohms when the ambient light level changes from 0 lux to 100 lux. We have to design a signal conditioning circuit that turns on an alarm system or an LED light when the light level drops below 20 lux, and turn it off when it increases from 30 lux. So you are turning it off at 20 lux and you are turning it back on after 30 lux. So there is a dead band or a hysteresis in your design. So just by reading up to this point, we can determine that we have to use a hysteresis comparator. Then you have only a 5 volt power supply. Okay. Make sure the power consumption of the sensor doesn't cross 5 milliwatt. So yes, this is a resistive sensor and you have to keep in mind the power dissipation across the sensor. Otherwise, it can change the behavior of the sensor because the temperature change can change the value of resistance as well. But we do not want that. You have to provide the reference voltage for defining the threshold light intensity using DAC. All right, give the digital input value that is to be given to the DAC input to generate the required analog reference voltage. All right, so this is a fairly complete design problem, and let's try to solve it step by step. So range of interest of your light level changes from 0 lux to 100 lux, and the resistance of your sensor changes from 3000 ohms to 1000 ohms for 0 lux to 100 lux. This gives us a slope of negative 20 ohms per unit lux. So this implies that the resistance at 20 lux is equal to 2600 ohms, and the resistance at 30 lux is equal to 2400 ohms. We have to convert these resistances into voltages. So let's use a potential divider for that purpose. So here is our potential divider. This is our 5 volt supply. Let's choose this to be the fixed resistor and this to be your LDR. And here is your V out corresponding to your varying light intensity. So the maximum power consumption of the sensor shouldn't cross 5 milliwatt. This means that P is equal to V out squared over LDR should be less than or equal to 5 milliwatt, and V out is equal to LDR over LDR plus R into 5 volts. This implies that 25 LDR square over LDR plus R into LDR should be less than or equal to 5 milliwatt. Cancelling this square with the LDR, we have when LDR is equal to 1000, R should be greater than or equal to 1236 ohms. And when LDR is equal to 3000, that is the maximum value of your LDR, R should be greater than or equal to 873 ohms. This implies that R should be greater than or equal to 1236 ohms to satisfy both the boundary conditions. So this means that we have to choose a resistor that this fixed resistor whose value is greater than 1236 ohms. So choosing R is equal to 1300 ohms. So this R is equal to now 1300 ohms. This means that at 20 lux, V out is equal to 3.33 volts, and at 30 lux, V out is equal to 3.243 volts. Turn on the LED when V out is greater than or equal to 3.333 volts, and turn it back off when V out is less than or equal to 3.243 volts. So this means that your delta V is equal to 0.09 volts, and that is equal to R over RF. So we are using a hysteresis comparator. This means that let's choose RF is equal to 50 kilo ohms and R equal to 900 ohms, and this will satisfy this expression, and also that RF is much greater than R. So let's try to make this circuit now. Here you have your potential divider. This is your LDR. This is R fixed, that is equal to 1300 ohms with a 5 volt supply, and this is going through an input resistor to a hysteresis comparator's positive input. The negative input is connected to the reference voltage. We'll come back to that. Ri is equal to 900 ohms, and here we have a feedback resistor Rf that is equal to 50 kilo ohms, and here we are getting our V out that is connected to an LED light. So the solution to our problem is almost complete, and here we need a Vref equal to 3.33 volts, but the remaining point is that we have to provide this 3.33 reference voltage using a digital to analog converter. So this means that we have to connect it through a DAC. So this is our digital to analog converter. Let's choose an 8-bit digital to analog converter with a Vref for DAC equal to 5 volts. Also we only have a 5 volt power supply, and we have 8 inputs. So this is your LSB, and this is your MSB. So for a 5 volt reference, the V out of DEC is equal to V out is equal to X over 256 into 5 volts. And for a 3.33 volt required V out, we put it equal to 3.333 into X over 256 into 5 volt. And this gives us X is equal to 170.6. So as it is a whole number, let's choose X is equal to 171. And this is your digital value that you have to supply here. This is your X. So 171 in binary number is 10101011. If you round it off to 170, it would be equal to 10101010. So this is the complete figure of your digital signal conditioning circuit. And which application is it used for usually? This is a computerized system to control your street lights. So now in this system you can see that this LED, this is your street light. So at the night time, as soon as the light drops below 20 lux, this street light will turn on and it will remain on until the light level reaches again above 30 in the morning. So it will be turned back off at that point. And that value of lux, that value of reference light is set by your digital to analog converter, and it is provided by a computer. So that's it for your lectures related to digital signal conditioning. I hope these design examples will help you understand the concepts in digital signal conditioning circuit design in a better way, and it will also help you to practice those concepts on your own. And in the next lecture, that will be the final lecture of the recorded lecture series, we are going to inshallah discuss the voltage based sensors and the thermocouple. So we are going to solve two very detailed problems related to that part of our course. So that's it for today's lecture. See you in the next slide session, inshallah. Until then, take care, stay safe. Allah Hafiz.